Welcome to Energy in Your Ears, the podcast hub of IEECP. This special series marks IEECP's 10th anniversary, and over the course of 10 episodes, we will highlight key themes central to our work, from housing inclusivity and local energy governance to building renovation, one-stop shops, industrial efficiency, and many more. I'm Anousheh Parsaei, communication expert at IEECP, and your host for today. In this episode, Turning Industrial Waste Heat into Climate Solutions, we explore how waste heat can be transformed into a powerful tool for decarbonization with perspectives from the REWITCH and ODYSSEE-MURE projects. Today, I'm joined by Pia Manz, researcher at the Department of Energy Technologies and Energy Systems at Fraunhofer ISI. Pia had contributed to the last phase of the ODYSSEE-MURE project, where she has written a policy brief about industrial excess heat and the role of efficiency in the EU. Our second guest is Andrea Frazzica, senior researcher and project leader at CNR. He is also project coordinator of REWITCH. Thank you both for joining me in this episode. To start, I would like you to briefly introduce yourself. Pia, please go ahead. The floor is yours.
Hello and welcome also from my side. I'm Pia Manz, researcher at the Fraunhofer Institute for Systems and Innovation Research in Karlsruhe, which is in Germany. I studied renewable energy engineering and I joined Fraunhofer in 2017. I recently completed my dissertation about the potential of district heating in the EU. And during my thesis, I also looked at the industrial excess heat potentials for district heating today and also in the future. For that, I applied several energy system models covering the regional energy demand of industry and buildings. And yeah, as we apply applied research at Fraunhofer ISI, we also work on deriving policy measures from our analysis.
Over to you, Andrea.
Thank you very much, and thank you again also for inviting me in this nice event by IEECP. My name is Andrea Frazzica. I'm a senior researcher here at CNR, which is the Italian National Council of Research, the largest research public body in Italy. Actually, CNR is quite widespread across Italy, and our institute is located in Messina, which is, let's say, in Sicily, and at the top right of the island in the closest part to the mainland. More specifically, our institute is working on advanced energy technologies in general, and our research group is mostly focusing on recovery and reuse of thermal energy solutions, so in terms of thermal energy storage and conversion. And in my case, I have a background as a materials engineer with a graduation, let's say, in many years ago, I would say. And I started from the very beginning working in the lab, developing new materials for thermal energy storage and conversion solutions. And now I ended up in coordinating the EU-funded project REWITCH, which is about demonstrating large-scale innovative waste heat-driven cooling solution for industrial applications. So I would be very happy today to better introduce the project and go in deep also in the discussion with Pia about the activities we are going to perform inside the project.
Thanks a lot. Let us start with the basics. Pia, when we talk about industrial heat, excess heat, what exactly do we mean? Where does it come from, and how can it be used?
Yeah, excess heat is often also called waste heat. So I think we use both terms now here. So excess heat is simply heat produced by a system but not used. Very simply. It includes both sensible and latent heat. So in industry, this typically comes from production processes, often at high temperatures. But there are many other sources too, like not only industry, like waste incineration plants, power generation, wastewater treatment, service sector, and also in the future, increasingly electrolyzers, data centers. And these typically also produce heat at lower temperatures, but now let's look at industrial excess heat in this episode. But first, more general, we can look at the excess heat potential in several ways. So there's the theoretical potential, which is like the maximum possible potential. Then there's the technical potential, accounting for technical limitations. And then there's the economic potential, which includes the costs or cost considerations. And on top of that, some literature also uses the realistic potential, then which also factors in barriers to actually using this excess heat. Then we can also classify excess heat by the form in which it's existing, or how we can find it. So it can be carried by flue gases, by solid materials, or like hot coke, rolled steel, the clinkers, or the product which is produced, or by liquid streams like wastewater, e.g., for example, from the paper production or from cooling water, or it can simply be lost through radiation or conduction from hot equipment surfaces. So one of the biggest sources of excess heat is the flue gases from the fuel combustion in furnaces and boilers in industry. So the flue gases or exhaust gases are the combustion gases that leave the industrial furnaces, ovens, boilers, steam generators, and are often released into the atmosphere unused. One thing to consider is they contain the reaction products of the fuel and the air, so also the residual substances like sulfur oxides and particulate matter. Okay, how can it be used? The excess heat can be utilized on site, so within the industrial site by other heat sinks with lower temperature demand, or for preheating purposes for high temperature processes, or also then excess heat can be utilized externally, so often by supplying a district heating network. Yeah, in short, almost all industrial processes have heat demands and then also heat losses. So there's untapped potential waiting to be harnessed.
Great. And looking across Europe, how big is this potential? What sectors or industries stand out as the biggest contribution of excess heat?
Yeah, across the EU, there are a lot of studies that look at the industrial excess heat potentials, and they estimate excess heat anywhere from about 80 to 800 terawatt hours in 1 year. So a large range, which is due to like different system boundaries. So what processes are looked at, definitions, what is excess heat from flue gases or the other forms I mentioned, or also the methods, so data availability. In our analysis of energy-intensive industrial sites, we found excess heat potentials of 116 terawatt hours in 1 year. But yeah, there are different conditions. So this is if the heat is recovered at high temperatures. For the context, to have a feeling for the numbers, the total final energy demand of industry is around 2,200 terawatt hours in 1 year in the EU of industry. So our numbers are at the low end of industrial excess heat potentials, but still, this is a significant resource waiting to be utilized. So looking at which processes actually have the highest excess heat potentials, this is typically processes with high temperature needs. For example, steel making, cement production, glass, aluminium, paper production, the chemical sector, and oil refineries, they all have large amounts of heat that currently often is not used. Looking at the individual sites, refinery and steel sites often have the highest potentials itself. But the number of sites also matters, so how many of them are actually in the EU. The non-metallic mineral sector, so the glass and cement production, they may have lower excess heat per plant itself, but there are so many of them across the EU scattered around. The combined potential is the largest overall. But to consider the sites I mentioned here mainly capture the large high temperature processes, while smaller plants and lower temperature sources like from the food industry or metal processing are left out. So the potential could be greater.
Great. Andrea, your project research focuses on turning low-grade industrial waste heat into something useful. Can you walk us through what solutions you're developing and in which sectors you're actually testing them?
Thank you very much for the question. Yes, indeed, Rewitch is trying to cover exactly that gap that Pia was mentioning. So the portion of waste heat that is the so-called low-grade waste heat, usually, let's say, around or below 100 degrees C. This waste heat temperature level is usually not possible to be easily recovered, especially if we want, for example, to produce power via organic ranking cycles or stirring cycles that are already close to the market. In our case, we would like to demonstrate that we are able to recover this low-grade waste heat and reuse internally in the industrial plant, mainly to provide cooling, so industrial cooling to the process. There are already, of course, existing technologies that are working on these temperature levels for these applications. But what is new in Rewitch is that we want to further, let's say, enhance the features of these technologies. These technologies are usually under the umbrella of the so-called sorption technologies that are basically standard cooling cycles. So chillers that are, instead of being driven by electricity, they are driven by heat at different temperature levels. In our case, what we want to develop are two different technologies that can further enlarge, let's say, the capability of providing cooling by this kind of technologies. More specifically, the idea is to develop three different new processes. One of these is based on the so-called adsorption technology, which is based in this case on a patented solution by an SME from Germany that is trying to make adsorption chillers more compact and more efficient, and especially to lower their cost once they will be ready for the commercialization. The other two technologies are instead based on the absorption technology, so on a slightly different concept, which is already on the market by a German company. But what we are going to develop are two different new cycles. One of these will integrate two different temperature level in terms of cooling to be delivered at the same time to the industrial process. So in this way, with the same equipment, profiting of very low grade waste heat, will be able to satisfy at the same time two different cooling demand at two different temperature levels. While the third option will be an hybrid solution. So in this case, we are going to integrate a compression cycle inside the absorption one in order to have the maximum flexibility to profit not only of waste heat, but also, for example, renewable power generated on site, and provide at the same time cooling and heating to the process. So kind of a cogeneration of heating and cooling at the same time. This is the overall aim of the project. What we are doing is not only developing these technologies from the technical point of view, so to prove their performances and their capabilities in real operation, but also to make them attractive for the market. So the idea is to already from the design evaluate the impact from the economic point of view, both capital cost and operational cost, in order to make them attractive ideally right after the end of the project. This is an ITRL project, so we are going to demonstrate these solutions in different demo sites. Probably I will have the chance to go more in details later on. But yeah, the overall our idea is to come to a final product that can be considered ready for the market immediately after the end of the project.
Very interesting. So Rewitch builds on earlier experience with solar cooling system, but now takes a step further by combining thermally driven sorption cooling with both solar thermal and industrial waste heat. Could you explain how these demonstrations work in practice and share some examples of the industrial cases where you're testing these solutions?
Yeah, thank you. Actually, as you mentioned correctly, we are working on this technology since many years. We had the chance in the past to work in other projects where we try to demonstrate I would say, more standard technologies, but coupled directly to solar thermal as a primary source. So to have a completely renewable cold production in industrial plants. This turned out to be technologically feasible. Of course, there are many challenges. First of all, as you know, solar thermal in general doesn't have a huge power density, which means that if you need to install a large cooling capacity, you also need to install a very large solar thermal field that most often is not feasible in industrial plants because of lack of space. But on the other hand, beside let's say the technical challenges, the most relevant barrier is represented by the cost of the system, because you are making, you are using novel solutions, novel technologies that are not fully established on the market. They are more expensive than the standard ones, and this is always the main barrier when you try to make them attractive for the end users. So what we would like to do in ReWitch is to kind of mix partially on-site renewables and waste heat that is available basically in every industrial plant, as Pia was mentioning before, and to make them, let's say, to mix them in the most efficient and techno-economic perspective for the end user. This means that the three technologies that I was introducing before will be demonstrated within the ReWitch project in 4 different demo sites across Europe. Our intention was not only proving them in standard industrial processes that are requiring cooling, like, for example, food and beverage, but also extending to other industrial processes where cooling usually is not considered as a main, let's say, driver in the decarbonization, but is still a requirement. So to go more in the details, we are going to demonstrate the adsorption chiller, so the novel patented solution, into different demo sites. One of these will be a brewery in Poland, where we will also install a small but relevant solar thermal field, and we'll profit of waste heat that is generated during the wort cooling of the beer production. So the wort cooling itself will feed the adsorption chiller, will provide cooling, and this cooling will be used for the fermentation of the wort. So this is a first approach to integrate solar cooling and waste heat cooling in a single process. The second technology, second demonstrator in which we'll prove the adsorption technology, will be instead installed in Italy in a paper mill in Tuscany. In this case, we are not going to exploit solar thermal, but only waste heat. And in this case, the waste heat will be recovered directly from air compressors. Air compressors are equipment that are installed in every industrial plant. So we'll basically exploit the waste heat generated by the air compressing unit to drive the adsorption chiller that then will provide cooling to electronic equipment and infrastructure inside the factory. The other two solutions, so the two temperature level absorption cycle and the hybrid absorption cycle, will be tested in other two facilities. The 2 levels absorption cycle will be tested in a biorefinery in Greece. In this case, they need to have 2 different cooling temperature, one for the maintenance of the biofuels, especially in summer when they have very high temperature in Greece. And the other one is to provide cooling to the process itself. This is happening at 10 degrees C and 20 degrees C, so we need to have at the same time provision of 2 different cooling streams. And this will be done at the same time by exploiting on-site waste heat from a cogeneration plant and solar thermal again installed in the plant. The final one is a dairy company in Spain. Is a very large cooperative there that is dealing with many different products. In our case, we will be integrated in the dairy part of the plant. And the hybrid chiller will exploit completely solar heat as a primary driving force, and will cogenerate at the same time cooling and heating for, let's say, hot water demand of the plant, especially for cleaning and pasteurizing the bottles of the process. And we'll use also a compressor, so it's an hybrid system. We'll also have on-site PV installed to cover the electricity demand of the chiller, and then we'll be able to co-generate heating and cooling at the same time. So this is, of course, the plan of the project, which started 1.5 years ago. So we plan to have the installation in the demo sites by the end of 2026. So hopefully the monitoring of the different plants will start in 2027. And yeah, this is what we are aiming at.
Thanks a lot. Now I would like to bring both of you in on the next points. Let's zoom out for a moment and let's discuss what policies are in place at the EU level to support the use of industrial waste heat, and how does progress in energy efficiency affect the role of waste heat, let's say in the bigger picture. Pia, over to you.
Yeah, maybe, as a more general remark, despite improvements in energy efficiency over the recent years in industry, large volumes of excess heat are still released into the environment. And even though energy efficiency progress will reduce maybe the excess heat in the future, the technical limits of the process mean some of this will always remain. And now looking at the EU legislation, it has defined waste heat and cold in the Renewable Energy Directive, so the RED III. I will cite it now very shortly. It's the unavoidable heat or cold generated as a byproduct in industrial or power generation installations or in the tertiary sector, which would be dissipated unused in air or water without access to a district heating and cooling system. And then it goes on. I will spare us this. But this definition makes clear where the focus of the EU legislation lies. It's using this resource in district heating. And then the other main EU legislation is the Energy Efficiency Directive, the EED 3. In Article 25, there are member states required to carry out comprehensive heating and cooling assessments. I will come back later to this role. In this article, there are also policies required that support installation for the utilization of industrial excess heat. They should be developed by the member states. In the next article, in 26 of the EED, it defines what counts as efficient heating and cooling, district heating and cooling. There are different definitions, but and there it's defined that it should at least, from the next years on, at least contain 50% renewables or excess heat. So it gives a role for excess heat in district heating and cooling. This article also requires new or refurbished large industrial plants and also data centers to make use of their excess heat whenever technically and economically feasible. And also in the request of the Energy Performance of Buildings Directive, so the EPBD, it includes this efficient district heating and cooling as defined above, as a possible source for the zero emission buildings. So it strengthens also here the role of district heating that is possibly supplied with excess heat. The question is now, how does rising efficiency affect all of this? On the one hand, industry electrifies in the future, phasing out the fossil fuels, and uses possibly more of its own heat internally. So efficiency progress, and this means the amount of excess heat will decrease, which especially when we look at the amount which is available for externally uses. The scale of that shift will vary by the sector process and is still uncertain. On the other side, when we look at the district heating networks, they themselves will become more efficient, operate at lower temperatures, which opens then the door to use more low temperature industrial heat that was previously unusable, or which is still unusable today.
Indeed. I agree with the approach by Pia, what she reported so far. In the end, I mean, is the thermodynamic that is giving us the rules. So any conversion stages will bring us, an inefficiency, a waste that often, especially in industrial process, is a waste heat. So probably with electrification, this will be lower, but still will be there, and we must be able to recover them to make the industry sector more efficient. In our case specifically, we are trying to exactly follow these directives, because which the main aim is to reuse internally the waste heat via conversion in cooling, and then using it either directly in the same industrial plant, but another option to reinforce the concept of industrial symbiosis is to have it reused inside industrial parks whenever it's needed by other industries. And this is feasible. It's something that is actually already existing in terms of industrial parks, but of course, what we are trying to improve is the conversion stage. So let's say the generation of the cooling to be provided to the other industrial partners, let's say. On the other hand, what we are also going to investigate, it will be more a replication study, so it won't be demonstrated in real plant, but mostly investigated via numerical analysis, will be the possibility to collect waste heat and cooling provided by the industrial plant and use it inside district heating and cooling networks. Again, this district heating and cooling network could be inside an industrial park, so can let's say still be used as industrial heating and cooling, or can be also used for providing heating and cooling to neighbor, for example, commercial and residential areas. So this is for sure the right way to couple the directives that are now in place with the novel technologies under development.
Great. Now I'm curious to know, what are the biggest barriers right now to making better use of this excess heat?
Maybe I can start, and then Andrea
Yes.
can give us more insights from
Woman
this
first.
project. Cool. Yeah, maybe the barriers, we can classify them into like 4 main categories. I will go through them, and then maybe you can shed some more light on this. First, there are the technical barriers. So, for example, the temperature of the excess heat doesn't match to what's needed elsewhere, or the temporal availability, so the supply is intermittent and not like the demand. Then also, of course, the infrastructure may be missing. So district heating, or maybe also for the districts or for an industrial park, you need like pipes. Or the existing plants may need also costly retrofitting. Yeah, this brings us to the second category. That's the economic barrier. So you have high upfront investments for excess heat utilization, often low expected returns, and also long payback periods. Third, then there are the regulatory barriers still. In many countries, there's no clear framework for connecting to district heating grids, no defined ownership models, and also unresolved liability issues, because you have a long-term energy delivery contract. Yeah, and maybe fourth, there's the awareness. So many companies, especially small, medium-sized ones, they lack the technical expertise to identify themselves and harness their own heat potential. So in many cases, the scale of the opportunity is just not clear. Yeah, overcoming these obstacles takes more than one action. It means technological improvements, targeted financial incentives, better regulation, and of course, greater awareness of what's possible with industrial excess heat. And maybe this brings us to Andrea.
Yeah, thank you. Yeah, of course, I fully agree. These are clearly the main barriers whenever we speak about recovering waste heat. I would like to add maybe one more, which is basically to convince the industrial owners to install new technologies. And this is possible only if you prove that your technology is not only, of course, efficient and economically viable, but also reliable. Because probably the main concern, if you speak to any industrial owner, is to be sure that their process is never affected by a new technology. So you can promise them to, improve the efficiency or even reduce the cost, but if in the end this poses any risk in the production, this is always their main concern, which is understandable because in the end they are making money out of what they are producing. Beside this, I mean, if I speak from our side, from Rewish side, of course, the main barrier is to be sure that the technology is working and is efficient and reliable operating. But as mentioned already before, we are already since the beginning targeting a reasonable price of these technologies. Otherwise, even the best technology will never be accepted because the upfront cost, I would say, even more than the operational cost, is always a risk. And this is always a barrier when you want to move from the research to the market, which is part of our job in this kind of projects, and we are trying to address this since the beginning. But we know that it's always in the end the final barrier before entering the real market.
As industries electrify and move toward climate neutrality, what role do you see waste heat playing in the future energy system?
Yeah, as I said before, the resource won't disappear, but yeah, it will change. Achieving climate neutrality means a big transformation in every industrial subsector. Maybe in short, I will go through the main transformation developments. The process heat will have to come from renewables if we don't use widespread CCS, but we don't discuss it here. So through electrification or also hydrogen furnaces. Second, then the process emissions from chemical reactions must be cut or eliminated. So especially from the cement production, where you have CO2 emissions from the process itself. And third, the material demand itself will shift if we increase the circular economy practices. And if you consider that. So in one publication and then also in the policy brief, I tried to quantify these effects by looking at the different processes. I'll try to make it short. So applying the best available technology, which is called, so to increase the efficiency, also recovering the heat internally inside the plant could decrease the externally available heat by about 40% on average. Then if you shift the production from primary materials to secondary materials, for example, steel, you have further reduced excess heat potentials, and then also switching from the fossil fuel furnaces to electrified or hydrogen ones. This will then cut the available excess heat by another 20%. And if you put all of these effects together, the excess heat that is available externally could drop by about 70% compared to today's potentials. So this is really the lower end, and if everything of these transformation steps will happen. So if we look then what's really available for district heating, it also depends on where will be future district heating areas. So where can we connect these industrial plants to the district heating areas? And if we look at the future district heating demand, it's about 1 to 8% of the heating demand, of the district heating demand in the EU that could be covered by the industrial excess heat, depending on the different assumptions for 2050. So of course, if you increase the district heating and you have more widespread areas, you could connect more industrial plants. And also, as I said before, if you have lower temperatures, you can reuse the industrial excess heat with higher efficiency and also tap the lower temperature potentials. But still, even though the numbers are not too high, so up to 8%, that means at the local level, if you look at like one industrial plant that feeds district heating, it can still cover a significant share of the district heating needs. Yes, exactly. But still, these numbers are looking at the energy intensive processes. So maybe, Andrea, you can complete the picture with the low temperature excess heat.
Yeah, thank you, Pia. Yeah, I mean, of course, as mentioned before, waste heat will be always there because of thermodynamics, so we cannot avoid this. What is clear is that probably it will be less compared to what we have as statistics now. Statistics are always varying, so we have different numbers if you look at different publications. But of course, what is clear is that the potential right now is huge. I'm not expecting this will decrease very sharply, but of course it will take time also to come to the real electrification. There are a lot of other barriers to have all this system electrified. But on the other hand, we need to consider that waste heat is not coming only from industrial plants. What we see, especially in the low-grade waste heat sector, I would say, is the huge growing of data centers everywhere. These systems are always needing cooling, which is the primary consumption, electric consumption in the end. And at the same time, they are generating a lot of waste heat, of course, in a temperature range that is even well below 100 degrees C. So it's even more challenging to recover, but there is a huge potential there. And I can already tell you that we already now receive many requests by data center owners to develop together with them new solutions especially for recovering heat and providing cooling. It's challenging, of course. Probably it will be our next challenge after a witch project, of course. But the idea is that if we are able to provide solutions that are technically sound and also economically feasible, this can be really groundbreaking technology, because the data center sector is for sure the ones that is growing by far the fastest level compared to other sectors. And in the end, there it's really unavoidable to have waste heat, because if you increase the computational capacity, of course, you also increase the amount of waste heat. This can be also used, of course, in district heating, so you can feed directly district heating networks. This is also what in this moment is probably the most attractive way, because you are trying to couple existing solutions like district heating to novel distributed sources like data centers, but still for them the cooling demand remains the main challenge. So having the chance also in this case to recover waste heat and reuse internally by cooling down the servers or the data centers themselves could be probably the next step for these technologies.
And finally, if you had to highlight the most urgent steps for policymakers, industry, researchers to take in the next few years, what would they be?
Yeah, from my point of view, so as I showed, the policies, both national and also EU level, they aim to boost energy efficiency in industry and to use the industrial excess heat in district heating, and also to expand district heating where it's cost effective. But still, as we already touched upon, there's a problem. We don't have a clear picture of where this heat is and how much of it we have there. And also the shift to climate neutral production makes those numbers of excess heat even less certain. So I would say this strengthens the need for EU-wide excess heat registration and reporting. We have that in some member states already, like Germany. But so this then enables the policies and the adoption of policies to address the full exploitation of the excess heat. Yeah. And yeah, then also regulating the third-party access to district heating and risk mitigation for the long-term heat delivery contracts, as I said before.
Yeah, from my side, I mean, I'm a researcher. I always say that the first step is to prove, if you want to have a new technology, to prove that this technology is really working and can be in the future a real market product. So this is to me always the first step, and this is what we are trying to do in REACH. On the other hand, of course, there is always the need of a push from the policy side. As Pia highlighted, I mean, there are already policy in place, but probably not covering all the needs. And we need to hope that the Green Deal will stay there to support this change towards in general, the decarbonization. This decarbonization does not only mean renewables. It can be also supported by the efficiency in industrial process, but in general efficiency in any process. So we really need to hope that this will stay for long and that they will continuously push on this, because it's a real need in different sectors. And beside this, of course, any novel technology, as mentioned before, must be also proven from the economic feasibility. So the other step to take is to show that these technologies are reliable, but also economically viable for the next integration in the market.
That brings us to the end of today's episode of Energy in Your Ears. We have heard how industrial excessive energy that is often wasted can instead become a valuable resource for decarbonization, or be recovered for electricity heating, cooling, or integration into district systems, whether through innovation technologies like those developed in Revit project, or through the data analysis and policy insights of ODYSSEE-MURE. Together, these perspectives highlight both the opportunities and, of course, the challenges ahead as Europe moves toward climate neutrality. A big thank you to my guests, Pia and Andrea, for sharing their expertise and insights. If you would like to learn more, you can find resources and links to both projects in the description of this episode. And don't miss our next episode, where we will shift focus to SMEs, small and medium-sized enterprises, and explore how they lead the way on energy efficiency, unlock benefits that go well beyond cost savings, and use standards to support effective policies with the insights from ODYSSEE-MURE 2050 project. Thanks for tuning in, and until next time.